All right, it is recording the right screen, so everything is good to go. And we are going to start the lecture. All right, so I hope you guys still remember that there's a homework that's due on Wednesday at noon time. Okay, so the homework is due before the class starts. Okay, um, I think most people should have started on it. Okay, even though it's due on Wednesday at noon, there's no actual quote unquote time limitation other than the due date, which means you could have opened it, just kind of look at the question, ponder, think about it, read the notes, see if you can come up with the answer. All right, so with that said, are there any questions about the homework assignment? No, no questions. Okay. All right. So if there are no questions about the homework assignment, and are there any questions about set notations in general? So that would include everything up to the Cartesian product. So do we have any questions about the concepts and the notations related to sets? No questions? All right. So without any questions up to this point, we are going to get started with functions. And functions is right here. Okay, this is it's the same kind of construct where I use GitHub to actually author the content. So once again, you can use the same trick that I have demonstrated. If there are, if you want to give yourself a test, like do I understand all the concepts? We have already illustrated how to use Gemini for that purpose. So we are going to get started here. It starts with a repetition of things that we have talked about already, which is in this case regarding tuples. Um, so this is basically just a repetition of what we already talked about in the previous class last Wednesday about tuples. So do we have any questions about tuples, the concept, and also, just generally speaking, what a tuple is, and and also how it is different from a set, how a tuple is different from a set. Do we have any questions about those? Okay, yep, go ahead. Yes, yep. So I will pay very close attention to braces, which we usually call curly because they're curly, as opposed to parentheses, which are used, for the purposes of tuples. Yep. All right. So we are going to continue to talk about functions. So in this class, when we talk about a function, it is not exactly the same, even though it is closely related to what you know as a function in math. So in general, we are basically just looking at a map when we talk about a function. Um, so there are a few things that we can talk about. I'm just going to kind of skim through my own notes, okay? Because I assume everybody had a chance to read the reading material before class, because that is actually important, or you will have time to read the material after class. So in this case, I'm going to focus on a typical way we define a function. F of x is defined as 2 times x. So this way we can apply f of 2 is going to be 4, f of zero point 0.5 is 1, and so on. So do we have any questions about functions defined in this way, which is typically what a math class will use functions for? It is essentially just a shorthand. So instead of writing a complex expression, we just say, oh, this is f of something. Yes, go ahead. So that may be the case in the case of a mathematical definition, but in this class, we look at functions as a set of tuples. So that means, we won't run into a problem of, oh, okay, it works for everything except for this one. Yep. So the way we define function is going to be, a little bit different compared to your math class. Okay. All right. So now we're going to go on and talk about the notation. So when we talk about a function, there are two distinct sets that we are mapping. the set that we are mapping from, in this case represented by X, is called the domain. So the domain is where we are mapping from. And then Y in this case is the representation of the codomain, which is what we are mapping to. In other classes, the name codomain is also called a range. Okay, but in this class, I specifically just use the term codomain. So if you have already understood domain versus range, all you need to do is to kind of remap, the word range to codomain. They mean exactly the same thing in this class. So going back to this notation, okay, this particular notation is Boolean, okay? It returns a Boolean value because it's basically telling you whether it is true or false that whether f is a function using x as a domain mapping to y as a codomain. So this is a Boolean, okay? This is a Boolean expression. It is either true or false, okay? So the true part is easy, right? The true part simply means, oh, okay, f is really a function. So the question is, how can f not be a function? In other words, how do we look at function in this class? So the way we look at function in this case is a function is really a set. So in this case, we are looking at an example here. F is, so using the example that we saw earlier, okay, let me see if I can show the earlier math definition and the set definition at the same time. So we are looking at this particular definition here. F of x is defined to be 2x. That's the mathematical definition. But in this class, we look at a function as a set of two tuples. And each two tuple maps a particular element from the domain to an element of the codomain. So let me just pause and see if that sentence is understood. Let me say that one more time. I usually cannot remember exactly what I said, so I can only approximate what I just said. So in this class, a function is seen as a set of two tuples. Okay, so right away we are using the terms that we learned last week. What is a set? What is a tuple? Okay, each tuple, which is each element of the set, within each tuple, the first item of the two tuple is an element of the domain, and then the second item of the two tuple is an element of the codomain. That is the minimum requirement of a function. It is a necessary condition for a set to be a function, but it is not a sufficient condition. So I just introduced a whole bunch of words. Each individual one is easy to understand, but do you understand, just the meaning overall? What is the difference between a necessary condition versus a sufficient condition? Is that concept understood? Go ahead. Yeah, correct. Sufficient condition means, if you meet one sufficient condition, then the consequent is going to happen. Yeah, so consequent is the right-hand side of an implication. Um, so if you have a sufficient condition, then the consequent, it guarantees, it guarantees the right-hand side. So that maps to the truth table. Hmm. Yep, that is correct. Yep, so very good. So yes, go ahead. Yes, they can. Yep. So we'll talk about in today's class we may not be able to touch that, but when we talk about injection, surjection, and bijection, then we'll be looking at the relationship between the cardinality of the domain versus the cardinality of the codomain. Okay, but yes, they can be different. Yep. Alrighty. Okay, so this is the kind of thing that you as a student need to pay attention to is when I say something, I try to be precise, which means most of the time, not always, most of the time the words that I choose is for a specific purpose. Okay, they're not just general words. A lot of times they have specific meaning, like what we just talked about earlier. Sufficient versus sufficient as a condition. Okay, so those are actually meaningful words in this class, and this is going to be the case for most STEM or math related classes too. Okay, each term has a very specific meaning. All right, so just to give you an example, okay, that we declare, okay, meaning that I claim that f is a function mapping from integers to integers, and it is defined over here like this, f of x is 2x, then we can also see at least a part of the memberships of f, okay? 0 maps to 0, 1 maps to 2, 2 maps to 4, 3 maps to 6, and obviously on the negative side, we have -1 mapping to -2, -2 maps to -4, and so on. Okay, so the total number of elements in the set is infinite because there's an infinite number of integers to begin with. All right, so moving on a little bit, okay? So using the notation that we have already talked about in uh, last week, okay, on Wednesday, this is the short form of saying if I want to define function f so that, f of x is 2x, and I want to use a set notation to define the same thing, this would be one of the ways to do it. Because what it says is whatever is to the left-hand side of the bar is the format of each element. So this is basically saying each element of f has is a two tuple. Of the two tuple, there's an x, but then if you know x already, then the second item of the two tuple is guaranteed to be 2 of x. Okay? The word vertical bar is such that, okay, so now we can limit where x can come from. X can only be an integer in this case. So is that notation okay so far? All right. And if you do not like the shorthand like this, okay, and you prefer to go all the way back to the more basic um, notations, then we can also go back to just using universal quantifiers. So this universally quantified expression is defining the membership of f, okay? In other words, we are using this side, the left-hand side of the if and only if, to define the right-hand side. In other words, we are trying to define what should be in and what should not be in f. So the way we say this is for every x that is an integer, for every y that is an integer, y equals to 2x if and only if xy as a two tuple is an element of f, which essentially says exactly the same thing as the earlier notation. It's just a little bit more spelled out. Do we have any questions relating to how the longer but more, kind of spelled out version is the same as the shorthand version, which is essentially saying f is defined to be 2x, but x has to be an integer to begin with. So all of those are basically saying exactly the same thing, but the notation is different. Do we have any questions? No questions? All right. So if anyone needs more time to formulate the question, which I understand, you can always just kind of raise your hand or give me a gesture, to go like, okay, I need a little bit more time. Okay, you can borrow your gesture or signs from football. You can say timeout. Okay, then I will understand and go like, okay, well, I'll give you guys like another 20 seconds or a minute or so to formulate your question, because it is important that you formulate the question and ask the question. Whether you ask me, okay, in the class, or whether you just write it down in your notes, and so that you can try to answer that question later. Either way is okay. Okay, you can just ask me in the class, or you can just write it down. But the important part is to notice that you have a question. to notice that, okay, something is not entirely connecting, okay? So I kind of need to write this down so I can resolve that, either later or I can ask the professor about it in class. All right. So with that said, we are going to say, okay, so technically speaking, what makes a function a function? Okay, so I know this sounds really kind of stupid, right? Because it sounds like it's a circular reasoning. So what I should have said is what makes a set a function? Okay, because there are sets, there are functions, and there are also sets that are not functions. So that's what I should have said, but this is more catchy. Um, all right. So if you are given that f is a function, x is the domain, y is the codomain. Let's assume that is given to you. We know that is the case. So the first thing that needs to happen, or one of the necessary conditions in order for this condition to be true, one of the necessary condition is this condition here. So I'm not going to spell it out, okay, even though I should have hidden the next sentence. I was about to ask you guys, what does it mean? Okay, well, but since most of you already read the next sentence, it means exactly that, okay? F is a subset of the Cartesian product between x and y, okay? Um, so one quick test that you can kind of self-assess right now is if you see this expression the first time and you go like, oh, I know exactly what that means, okay? Because I know the symbols already, then you are good. Okay, you are keeping up with the class, or you have prior knowledge before coming to your class. But as far as the symbols of set operations are concerned, you are good. Okay, you get you have the knowledge. If you're thinking, well, I know where to find in the notes, in my notes or in if in your own notes or in my reading material, you're still good. Okay, it means you have read enough or written enough that you know where to find it, even though offhand you may not remember the meaning of the symbols. On the other hand, for people who are thinking, I don't know what this means, and I don't know how to look it up to find out what it means, I would be concerned. Okay, we are only in week what 2 or 3 right now. Okay, and if people are already having that sense of not knowing the symbols, I would be concerned. Yes, it is a necessary condition. Yes. So this one here, where the mouse is pointing to, is a necessary condition for f to be a function mapping from the domain x to the codomain y. That is correct. Yep. All right. Well, since I mentioned the word, necessary, it implies that there are other conditions that also need to be true in order for f as a set to be a function from the domain x to the codomain y. Okay, so this is the kind of thing that you can think ahead is, if I use the word necessary condition instead of the word sufficient condition, then you automatically kind of, you know, look ahead a little bit, okay, in your mind and go like, if this is only a necessary condition, where are the other ones? Okay, that's the kind of mentality that you can kind of use when you're, talking about logic like this. All right, so the other condition is in English term, okay, so I'm just going to highlight the wordy version of that, okay? So in English terms, the other condition that needs to be true, the other necessary condition, is each element of the domain must be mapped to one and only one element in the codomain. Okay, so what does that mean? Okay, so I'm not going to go any further, and instead I'll give you a few examples, and you can tell me whether the highlighted portion is true or not. So we're only focusing on the highlighted portion. So I'm going to write the examples on the whiteboard. Okay, so you can copy it or you can not copy it, but it's not going to be in the video. Okay, even though I will still use my voice to kind of describe it. So we'll just assume X has the elements of 1, 2, and we'll assume Y has the elements of A, B. Okay? And we're going to look at F as a set. Okay? And we'll go ahead and look at A, B, and 2A, and then 1A. There we go. All right. So we have three elements in this F, okay, as a set, and they are respectively 1B, 2A, and 1A. So does this set satisfy the requirement of each element of the domain must be mapped to one and only one element in a codomain? So there are a few things, right? Okay. So all of these terms are important. Okay. What is the domain? The domain is X in this case, is where we are mapping from. What is the codomain? The codomain is where we are mapping to, which is Y in this case. So the other term that is really important now is what does one and only one mean? Yep, exactly one, right? It means exactly one, cannot be zero, cannot be two, it has to be one. Okay, so how do we know? Okay, so the key word here, okay, because it is a quantified expression, is a quantified statement. How do we know this is a quantified statement? The highlighted portion on the projector right now. Which word gives away that, oh, this is the quantifier and this is why it is quantified? Which word suggests? Nope. So let's read the whole sentence again, okay? Each element of the domain must be mapped to one and only one element in the codomain. Each, that is correct, okay? So exactly. So each is telling you that this is universally quantified. Okay. So when it's universally quantified, then we go like, okay, so that means we have to look at each and every element in the domain first. Okay. If one element in the domain does not meet the requirement, forget it. The whole thing doesn't work anymore. Okay. And that's why it's called a universal quantifier, because the everything that is quantified needs to make the expression true. Yes, go ahead. Nope, it does not mean it is unique. Yep. So yeah, one and only one does not mean unique. It just means exactly one. Yep. Go ahead. Say again. The one on the whiteboard. Yes. Mm, not purposely. I did purposely make this one the way that it is, but I did not purposely miss out the other one because the point that I need to make, this will make the point already. Yep. So so now so that's exactly the point. Okay, that's a very good question because you're asking what does it mean when I say one and only one? So that is the limitation of natural language. Okay, because the way we interpret phrases and words can be slightly different. Okay, and that ambiguity is going to cost us. Okay, because that's not good when we need rigorous or need rigor in the description of what we are talking about. Okay, so that's a very good question. Okay, what does one and only one actually mean? But before we go there, we're going to go to the quantifier. In other words, we're going to look at element 1 from X. We're going to look at element 2 from X. And I'll emphasize and say that, okay, this is in X, this is also in X, and these are the only two things in X. Are we Are we agreeing to this is enumerating all the things that are in X? Okay, it's one, two. That's it. Okay. So now we look at this one, and then we ask the question: is one mapped to one and only one element in Y? That really becomes the question. So you ask, okay, what do you mean when you say map? It means it's in a tuple. One is the first item in a two tuple, and then something is the second item. Okay, whatever that second item is in a two tuple is what is mapped to. So now the question is, what is one mapped to? One is mapped to B, but one is also mapped to A. In other words, one is mapped to two different things in the codomain, which means this requirement is not met. I can say false because one, which is an element of X, is mapped to two different things in Y. Is that okay? And therefore it does not meet the requirement. If one element is not meeting the requirement, and we need both of them to be true at the same time, or both elements of X to have the same property, if one is not meeting that requirement, then the quantified expression has to be false already. So we can now conclude that this f is not a function. Or you can say, in this case, okay, f being a function, mapping from X to Y is false. That is the conclusion. Are we? Yes, go ahead. Hmm? One is not in set Y. That is correct. It is what is false is no. It the false applies to one as a value in X. It does not map to one and only one value in Y because it maps to two values in Y. Two is not one and only one. Yes. So it maps to two elements in Y, even though they're all in Y, it's not one and only one. So that's why this particular function f, excuse me, I take it back. That's why this particular set f, the way it's defined, is not a function from X to Y. All right, cool. Question? Um, you can do it this way. However, I can give you another example where, you know, that test is not going to be useful. So even though the vertical line test is great for detecting this particular problem, it is not detecting all of the potential problems. So I will show you the next example. Okay, so visualization is a good tool, but we have to realize that certain things cannot be easily visualized. Um, Question? Yes, that's that is a necessary condition, but the highlighted sentence on the projector, that's also a necessary condition. So that means if a set is not meeting all of the necessary conditions, it is still not a function. It can be a set, it can have many properties, but it's not a function if unless it meets all the necessary requirements. Yep. Okay. All right. So can I change the example? For those of you who want to write this down, have you written it down? We good? All right. So we're gonna change this just a little bit, okay? So I'm just gonna do the super lazy thing, which is just doing this. And then we want to look at the conclusions again. All right. Okay. So now I just changed the set F to only have one single element, which is the two tuple of 1 comma b. I'm describing verbally so that people who did not write it down can still kind of listen to the lecture and kind of get an idea what we are talking about. Yes, but with certain restrictions. Okay, so the restriction is the restriction that we're focusing right now is the highlighted sentence on the projector. Hmm. Yep. Well, yes, not for every element in X. Okay, so for 1 as an element in X, we are all good, right? So if you ask, okay, is 1 as a value of X mapped to 1 and only one element in Y? The answer is yes, we're good, right? Because 1 maps to B, and is B an element of Y? Yes, okay. And is that the only one that it maps to? Yes, okay. So it has met this requirement, okay. But then we shift our attention to the other element that is also in X, okay, because each means that condition has to be true for every element of X. Okay, just having one element of X meeting the requirement does not mean the universally quantified expression itself is true. So now we have to look at the second one, which is 2. Okay, so now we ask basically the same question: is 2 blah 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 blah, which is mapped to one and only one thing in Y? We look at the set and we go like, doesn't mention anything about 2, which means 2 is not mapped to anything in Y, or you can also say 2 is mapped to 0 element or 0 elements in Y. So now the question that you have to answer is 0 the same thing as 1 and only 1? Nope. So we now say, this is false. Now, because you have at least one element that does not meet the requirement, that means the quantified expression or the sentence that is highlighted on the projector is false. So that's why F being a set with only one element, which is 1b as a two tuple in this case, means that F is not a function. Once again, this is false. Are we doing okay so far? All right. Yes. That is correct. Okay, that is a very good deduction. Okay, so the deduction, let me mention it in the recording and then I'll address your question. So the deduction is in a function, if f is a function, then the cardinality of the domain and the cardinality of f itself, they have to be exactly the same. Yes, go ahead. Well, well, let's do that. Okay, so I'm making the third example right now. So now we are adding back an element in F. So F now has two elements. It is 1b and 2b as two tuples. Okay, so there are two tuples in F in this case. So now we have to go back and reevaluate the conditions. 1 in X, okay, this is still true because we haven't changed that element in F. Okay, so we're still good. What about 2? Well, let's see. The question is asking, is 2 as an element of X mapped to one and only one element in Y? Well, it maps to B. So now the question is B an element of Y? Yes. So the real question is, does that count as one and only one? Yep, because one and only one is only for counting purposes. It does not suggest uniqueness. Okay, so that means we have true, okay, so which means the requirement of mapping to one element, one and only one element of in Y is true for all elements of x. So now we can make a conclusion and say that f being a function from x to y is true in this case. Yes. Question? That is correct. It can be. Yep. Y can have an element of C, D, E, F, G. It doesn't matter because according to this, we just need every element of X to be mapped to one and only one element of Y. It does not say that everything in Y need to be mapped to. So that's a good observation too. Okay, that's a good question to ask because you're already thinking, how can I break this? Okay, which is good because that's one of the few things that AI are not currently very good at is basically um think of the think about the negative space, okay, so to speak, okay, the part that is not said. All right. But I think this is also a good example from all the questions and all the clarifications that I was doing. It also illustrates how the English sentence itself is not exactly the most precise way of defining something. Okay, because it took us a few examples to truly illustrate what does it mean when you say for each element of X or domain, it has to map to one and only one element in the codomain. It took a little bit of effort to explain that. So now the question is, can we do this without using um, English? Okay, can we use only set notations to do this? That's the first question. The second one is, have we learned all the set notations that we actually need to express something like this? So there are a few questions. Okay, there are two questions. One is basically embedded into the other one. So what do you think? Yes. Okay, we have enough to give it a shot. Each one is easy, right? Each one is like, okay, universal quantifier done. What we really it's harder to say is can we count? Okay, because we need that one and only one, which means it cannot be zero, it cannot be two. If we say at least one, it means one or more. If we say up to one, it means zero or one. But we need one and only one, which means exactly one. The only counting mechanism that we have talked about related to sets is there's one cardinality. Exactly. Okay. So that means whatever we do, okay, it's going to have something to do with cardinality. Okay. So do you want me to reconstruct the expression from the ground up, or do you want to read the boring stuff in the reading material? Let's do it on the fly. Okay. I think that is a lot more fun. Okay. So I'm erasing all of this. Okay. And I'm going to derive the expression that we need to say exactly the same thing that is in the highlighted portion. Okay. Um, so let's go ahead and do that. All right. So remember what we said. The easiest part is the universal quantifier. Okay. So the universal quantifier is basically saying for every, I'm gonna say e. Okay. In x. Okay. We need blah 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 blah. Okay. So that whole blah 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 is saying that e, that whatever the element of x we have chosen to look at that particular point, that thing has to map to one and only one element in the codomain, or in y in this notation. So we are going to assume x is the domain of the function in question, and y is the codomain of the function in question. Are we good so far? Just in terms of the symbols. Okay. And we also identified that counting can only be done using the cardinality operator. So we are looking at the cardinality of something being exactly one. Is that okay? Because we are counting, okay? Because we are counting, map to one and only one in the codomain. But the phrase one and only one means we're counting, and it has to match exactly one. And the only mechanism that we can use for counting is cardinality. Okay. So now the question is, what kind of a set do we put inside the cardinality sign? So far, we have three sets. Okay. We have X, we have Y, and then we have the set in question, which is F, right? So we go like, well, cannot be any one of those because the cardinality of those are not limited to just one. Okay, so that means whatever set we are looking at that we need to count the membership, it is going to be created on the fly. Okay, if it's created on the fly, it's going to have the braces. Okay, because we are basically creating a set on the fly. We can call it ad hoc if you want. So now the question is, what kind of a set are we creating? There are a few ways to look at this. You can look at this as a set, okay? So we know if we're creating a set on the fly, there's a vertical bar, which means such that, okay, in English. Um, since we're counting, what E can potentially map to, there are a few ways to do this, but I'm going to choose the more direct way to do it. Okay, so the more direct way to do it is simply say, okay, each element in this set that we're creating is going to be a two tuple, but there's a restriction already right here. Okay, the first item of the two tuple has to be E. In other words, we're focusing. Tell me which element of X we want to focus on, and we need to make sure that the two tuple that is inside the set that we're creating, each two tuple must start with E, cannot start with anything else. But the second item is going to be quote unquote unbound or floating. It can bind to anything that meets the requirement that we're going to specify after the such that. So we're going to go like, we'll just call this F, okay? But F is not bound at this point. There's nobody says anything about I shouldn't use F because F is the name of the function. So sorry, okay, because I need to change this to something else. Let's use K, okay? We'll use K here. Okay, so K is really just a placeholder, okay? It's a placeholder of the second item of each two tuple that is in the set that we are creating. This particular set has no particular name. I just created it on the fly, okay? So it is anonymous. If you are um, if you have programmed in JavaScript, the concept of an anonymous function is not new to you, and we are basically having an anonymous set that we are creating on the fly here. Okay, so what about how do we restrict what K can possibly be? Well, instead of restricting K, we're going to restrict the two tuple entirely. We're simply going to say, oh, guess what? EK as a two tuple has to be an element of F. Done. Okay, so if I were to kind of make this more concise, so you can copy the whole thing already, it's already correct, but just for visual, I'm going to kind of simplify the whole thing a little bit just by closing the unnecessary white gap in between here. There we go. So this expression that we're looking at right now on the whiteboard is essentially the mathematical notation of the highlighted sentence on the projector. Are we understanding, making the connection or not? Yep, it is. It's representing. So EK together is the format of each element of the set that we are creating. E is already a constraint because we are already saying, okay, but E is already constrained because E is the element from X that we are evaluating at that particular iteration. But K is floating, which means K can bind to whatever. And we need every element remember the notation of this particular set notation here. It means for all E and for all K, E has to be in X and K, and then EK as a two tuple has to be in X. That's the other way to look at the set. E, you first, and then you go ahead. But you cannot because that is necessary to specify for each element EK in the set. EK has to be in F. You need that for this format to work. Because this is saying every element needs to look like this. This is saying that element has to be an element of F. Is that okay? One is defining the template of every element in the set that we're creating. And then the other one, the part that is on your right hand side of the vertical bar, is saying, oh, but we cannot just take any two tuple. That two tuple has to be blah, 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 blah. In this case, it has to be an element of F. Okay? Uh, you and then back you. Yep, go ahead. Hmm? Okay. So, okay, yes, we have three vertical bars, but because of the syntax of where the bars are, this bar is inside the braces, and the location of this bar means it means such that. The other two vertical bars is surrounding a set. So from the syntax, it means cardinality. That is correct. It's kind of like plus and plus plus are two different operators. Exactly. It has to do with the position. Yep. Okay, there was another question back there. Nope, not anymore. Okay. So, but you can also use a type perspective. You can only take the cardinality of a set. This bar here, this the nesting already says this vertical bar has nothing to do with this vertical bar here because this one is inside the brace. Can which operator, the pair or the single one? In this class, I only use this inside a set when I need to create a set on the fly. Yep. All right. Any other questions? Okay. Another question? Nope. Okay. All right. But are we seeing how this expression that I am showing on the whiteboard is doing the same thing as the highlighted sentence on the projector? No, the equals one is needed because without the equals one, what are you doing with the cardinality? Yeah, yeah. So even if you take into consideration that's in C and C++, an integer can be interpreted as a Boolean, but two is true too. So that means you kind of have to lock it down to equal to one because that's the only value that we are looking for. Yes, for such that is not an operator like that. It's more like a separator to separate the template of each element in a set that we are creating from the requirement of that element. Yep, yep, yep. And for those of you who think, I do not like the way this looks, Okay, because we typically want to have a single letter to represent each element, but this one is using a two tuple instead of just a single letter, a single unknown. Okay, fine, we can do it in a slightly different way. Okay, we keep all of this stuff here, and then over here we just say, let's pick another one. I think G is okay in this class. So I'm going to say G, okay? So this is saying, okay, for each element G in this particular set, the following has to be true. So what following have to be true? We just say that, the first element of G, okay, has to be E. So I'm borrowing the indexing operator, okay, to address, n element of a two tuple. So we go, G0 has to be E, and um, ng has to be an element of f. Okay, well that works the same way. So these two expressions are basically the same. Either way, you need this a little bit of complexity because we have to say, every element in here is a two tuple, and that two tuple has to be an F. But we also have to single out the first item of each two tuple and say that has to match E. So, no matter which representation you use, you still need to be able to specify the constraint of the first item of each two tuple has to be E. You got your hand up? Uh-huh. No, because that is implicit. That is already implicit. Okay, so the question is, do you guys remember this notation? It is a template that we use in this case. In other words, everything from the middle vertical bar to the end of the set notation is the predicate. It is specifying the requirement. Okay, what qualifies to be in the set? And then the X, before on the left-hand side of the vertical bar is really just saying, okay, which funky variable name do you choose to represent each element of the set? So this notation can also be used without, we can get away without using this notation. But if we do that, we have to use a name. It cannot be anonymous. Because to say this, okay, so let's just say that this is our set V, okay, for no particular purpose, okay, we say this is V. This definition is symbolically the same as, okay, it is the same as saying for all x in the entire universe, okay. I don't care whether x is an integer, a real number, tax card, the department, whatever, okay. The requirement is p of x if and only if x is in V. So these two are the same, but this notation does not need to name the set that we're generating, but to use this notation, we kind of need that name, which is a little clumsy. Yep. And if you have no experience with anonymous functions, you would not appreciate the convenience of anonymous functions because you can just go like, I need to pass this callback, right here, and it's a one-use thing. I don't want to have to give it a name. That's how you can do it. Yep. All right. I thought I saw a hand earlier. No one. Okay. So are we ready to move on? All right. So notations are important, okay? Because now we can just this is basically going through the same thing that I was talking about, except I use Q instead of K. Okay, the slight difference here, but it comes to the same conclusion. Okay, so the notes actually explain the whole process of how this whole thing is derived. Okay. Now, if I have to say, what is important in this class, I would say the reasoning between, okay, so let me go back to the highlight. The reasoning going from the highlighted sentence to the final form, the reasoning is actually more important than the final form itself. Okay, because because you can see how I think about this. Okay, I try my best to kind of verbalize the thinking process. Are we okay so far? Okay, all right. So the next question is, but this is a really awkward way of defining a function. So why do we need to do this? Okay, so that's basically the second part. But before we get to that part, I'm gonna take roll because I forgot to do that. I need to set up an alarm to remind myself, but that's okay. I just have to change the times to give you guys a little bit more time. So let me go to here. I think most people can still do it, but I'm gonna give you more time. Okay. All right. So we have until 1:10 to respond to this. So click save, and then I have to unhide it. There we go. So if you wait, there we go. So if you have signed into Canvas already, just refresh your screen. You should see 2026-0202 row taking, and it does not seem to have a access code. Oh, it does have an access code. It is one. Big surprise there. I should have made it one and only one. Camel case. You cannot see it. It should be visible. It says it's published. Are you on the school Wi-Fi? If you're on your 5G, you may have a problem because I did turn on the IP filter. Okay. Yeah, the browser caches stuff, and there are two refresh too, by the way. So there's control R, and then there's shift control R or control shift R. Yeah, there are two refresh. I think they're slightly different. Alrighty. Yes. Yes. It is for the entire district. Yeah, this is for the entire district. No, it's more than that. 2 to the power of 16 would be a good approximation. That's like 65,536 exactly. But certain IP addresses cannot be used because the 0 and the 255 and the 254 are usually reserved for something else, like the gateway or the name server and whatnot. So the actual number is going to be about, I'm going to guesstimate about 40,000 ish. So are we all good with road ticking? Is anyone still doing it? Are you okay? Are you good? Oh, okay. Alrighty. Cool. So now we go back to this note here. Why is it important? So I am going to use a homework assignment as an example. Okay. So let's just say that you are taking somebody, okay, not you, because you took that class already. So let's just say that somebody is trying to take the class CISP 360, okay, and they're trying to write, the professor is trying to make an assignment out of a sorting algorithm. Okay, you go like, we know sorting already. Yes, I know that. So let's just say that I want to specify, I want you to write an algorithm that sorts an array in place, okay? Which means the array that I give you is the one that should store the sorted value from the original version of that array. You can use whatever temporary space that you want, but I just need the result to be back in the same array that I gave you. Okay, but in between you can use You can use an algorithm that is big O of n squared if you want to choose something that is insanely inefficient. So I don't care. I don't care how you do it. I just want to tell you what the result is supposed to be. Okay? So I can just say, well, the effect of this program is to sort the input array in place. Okay, that's one way I can specify. But what if somebody told me, but I don't know what you mean by sort. Can you define, what a sorted array, looks like, okay, in mathematical terms? So how would I qualify, what is the action of sorting? Yeah, in relation to the original array, because you can only define what a sorted array looks like in relation to the input. Because I'm not, okay, so I can give you a few examples. Okay, this is fun. This is going to be fun. And you can use this approach and try on other professors. Just don't tell them that you learned from me. And obviously, this part is being recorded too. And I'm too lazy to go back to my own recording and just kind of bleep out a portion. Okay, so let's just say that the assignment says, okay, this is your input array. Okay, so I'll give you what the input array may look like. Okay, let me. Uh, this is not erasing very well. Eh, I can just use a text editor to say the same thing. For this part, it's easier or quicker for me to type. Let's see. Accessories. There we go. Just need to make it clear. Hmm? Oh, I like NeoVim. I like the CLI version too, but okay. Hmm? Only when I need to. All right, so we'll just say that input of the array, so I don't even give it a name. So the input is 5, 6, 5, 6, 8, -1, and it will give it 3. Okay, so there are only 5 elements. Okay, this is the input. So let's just say that I was lazy on that day and I just go like, okay, give me an algorithm so the output is sorted. Okay, that's all I said. Okay, so in that case, the homework assignment, the output is going to be, and I don't even need to match the number of elements because I didn't say anything about the number of elements. This is sorted. It is sorted in a non-increasing way or non-decreasing too. But you cannot say it is not sorted. I have met all the requirements. If the only requirement is give me an output in the same array that I gave you that is sorted, this meets all the requirement. It is sorted. You go like, hmm. Okay, so let's just say the professor now gets a little bit annoyed and go like, okay, let me tell you what it means by sorted. Okay, and the professor goes like, and this time I'm going to use a mathematical notation so it cannot be misunderstood. So the mathematical notation goes like this. So let's just say that we hard code the whole thing to only have 5 elements. Okay, so let's just assume that that's hard coded. So the professor will now say for every I that is in the set of 0, 1, 2, 3, and yes, not 4, okay, the following has to be true. Okay, and this time I have to name the array. So we'll just call the array A for array. Is that okay? That's just a name. So we now have to say, okay, A of I has to be, we're going to use a non-decreasing order. So it has to be less than or equal to A of bracket I plus 1, close bracket. Okay, so let's just say the professor do something like this. This is useless. That output meets that requirement already, right? So now the question is, how do you at least relate the input array to the output array? Okay, so the first thing we need is notations. Okay, So we go like, okay, this doesn't work. Okay, so now we have to make it a little bit more refined. We're gonna have to say for the input, okay, we're gonna say the same thing, almost the same thing for every I in the set of 0, 1, 2, 3, and 4 this time. We are defining, okay, this time we're defining some constants, okay. So we're defining the constant of k underscript subscript I is defined to be a in square bracket I over here. In other words, I'm using k of I to remember um, the value of an item in the original array. So K0 is A0 originally before the sorting. A1 is K1 is A1 before the sorting. K2 is A2 before the sorting, and so on. So now I have a way to go like, okay, the output, okay, so now I can specify the output. So the output is going to be something like this, okay? For the output, I need the first one first, okay? So we're going to say for all I in 0, 1, 2, 3, I'm going to use exactly the same thing. So I'm just copy and pasting right now. Okay, this is one requirement. And now we go like, okay, but I'm smart this time. And, okay, so and what? Okay, and we'll say, for every I in 0, 1, 2, 3, 4 this time, we're going to say there exists a j, okay, in 0, 1, 2, 3, 4, curly, okay, such that, okay, um, a bracket I equals to k of j. In other words, for every element of the output, you have to find something to match it from the input. Okay, so it looks like this is going to work, right? But I can tell you it's not going to work. Yes, add the second element. It has to be 4 because there are 5 elements in the entire array. The only reason why we only limit to 0, 1, 2, 3 when we want to specify the ordering is because in the ordering, we have I plus 1 as the index. So that's why you have to stop one short. Yep. Okay. But even with the second version, it seems like, oh, we are fixing all the problems. No, we have not fixed all the problems. So let me give you a scenario. Look at the screen. So in this case, if the input, okay, I keep the same input, okay? So the input is the same, but this time we have this fancy quantified expression and the fancy way to referring back to the original array values. So for the input of 5, 6, 8, -1, and 3, this is all I need. Output 5, 5, 5, 5, 5. Done. Because, well, ask this question. Okay, is element 1 matching one of the initial values of the input array? Yes. Then you move I up by 1. You look at the second element, which is also a 5, and you ask the same question. It gives you the same answer. You look at the third element, you ask the same question. It gives you the same answer. I have met all the requirements. Give me my A. You can kind of see how I can be the most annoying student in the class. Yes. Then you have then you cannot allow the same value to appear twice in an array, which normally a sorted array can allow. It would address this particular part, yes. Yeah. But you're changing the premise of the original assumption of what can be, the property of the input array. It would complete this assignment because if you enforce less than, then the original array cannot have duplicate values. In other words, if I change the original here and I put a 5 here instead of a 3, That is valid as an input to a sorting algorithm because a sorting algorithm should be able to sort in an array that has non-unique values. So if you specify the extra thing of the array cannot have duplicate values, then yes, that would fix the problem. Okay, but on the other hand, if we just use the general interpretation of the input to a sorting array, then we cannot use that to fix the problem. Is that okay? So now the question is, how do we fix this? So the way to fix this is to use functions. So I'm going to show you the template of the function, and then we'll kind of continue to talk about a little bit I'll continue the discussion a little bit. So the way to fix this is to erase this. Yeah, I'll just erase this part here. And then the way to do it is to say, and there exists, okay, so quantifiers. So we're going to say there exists a function f, okay, that is mapping the set 1, 2, 3, 4, 5 to the same set, okay? 1, 2, 3, 4, 5. No, no 5, okay? Just 1, 2, 3, 4. 0, 1, 2, 3, 4. And f is bijective. Now you guys go like, but we haven't talked about what is bijective. That's kind of the whole point because this is why we need to talk about bijective, okay? But knowing that we have a function f and f is bijective, then we can now specify the last requirement, which is to say that for every I in 0 to 4, 1, 2, 3, 4, then we can now specify, a bracket I has to be the same as k of, okay? So this is where we use the f, okay? F of I, there we go. And then close paren, there we go. Yep, there you go. So bijection means um, it can go both ways, okay? Which implies a few things, okay? But those are the things that we will probably talk about on Wednesday. But this is the reason why we need to talk about functions. That's one of the reasons, not the entire reason, but this is one of the reasons why we have to talk about functions and also talk about what is injection, what is surjection, and what is bijection. For those of you who cannot wait, okay, bijection is also known as what is it? I think it is called a one-to-one. Yep. It's not but it also needs uniqueness this time. You cannot have everybody mapping to the same thing. It has to be, there's a uniqueness to it. Yes, it means f has an inverse, has an inverse. Yep. All right. Well, we still got 7 minutes, so I'm going to start to get into those concepts. What is injection and what is surjection? So we are moving on to the next module. All right, so let's go back to the notes. So this also means I can give you another homework assignment. So now you have, between now and Wednesday, you have two concurrent homework assignments going on. So the second assignment is called just functions. Okay, so that's your homework assignment. It is due in a week. Okay, so there's still plenty of time to do this one, but you just have to remember to do it. Okay, so now we're getting into injection, surjection, and bijection. All right, so I'm starting to use, a few different ways to say the same thing. So injection, okay, so this time we're assuming f is a function to begin with. It does not make sense. If S is a set of two tuples, but it's not a function, you cannot call a non-function an injection, okay? So at this point, we're going to assume that f is a function already. Okay, this is a function of interest. We know it's a function already. Then we have some additional requirement. This particular part is the additional requirement in order for f to also be an injection, or we can also call an injection as an injective function. So what does it mean? First of all, do we know all the symbols in this expression? Yeah, we got quantifiers, we got set in notation, not equal to, we got implication, we got not equal to, and then we have function applied to a particular value. I think we should understand all the symbols already. So the next item is, well, if you understand all the symbols, do you understand the structure itself? Okay, what does it mean? So what that means is if I choose an element p of x, I choose an element q of x, p does not equal to q implies f of p does not equal to f of q. Yes. Yeah, it depends on the function, and that's why some functions are injections and some functions are not injections. hmm So, if you look at this, okay, the first thing we want to do is, can you show me some examples? Okay, so we'll go ahead and take a look at some examples. So I'm going to say x equals to 1, 2 again, y equals to ab, and this time f is known to be a function already. Okay, so we'll have 1a, 2a. All right, so I'm going to put this on the side so you can evaluate whether this extra requirement is true or not for this particular definition of f, x, and y. Okay, so now the question is, by the time we get to the p and q, by the time we get to this expression here, how many pairs of excuse me, how many pairs of pq values are we looking at? Nope, there are four. There are four of them. Because P only needs to be an element of X, there are two of them. Q only needs to be an element of X, there are two of them. 2 times 2 is 4. Is that okay? All right. So, okay, so I'm going to give you a table. Okay. So, in terms of the P and the Q, P can be a 1 or a 2. Q can be a 1 or a 2 when P is 1. Oops. Ah. Oh, uppercase. There we go. So Q can be 1, 2, 1, 2. Are we okay with this? Because nothing says, okay, that P and Q cannot be the same thing. Not in the quantifiers, okay? Later on, we have some expression to kind of say, if they're the same, don't worry, we don't have to think about it, okay? So now we look at P does not equal to Q. Okay, I'm going to use the notation here. So uh, this is false, or I'm going to use 0 to mean false here. This is true, this is true, and this is false. Okay. P does not equal to Q is the left-hand side of an implication. What happens to the implication when the left-hand side is known to be false to begin with? The implication itself is true. Okay, very good. So that means here whatever we need to evaluate next, okay, which is P does not equal to Q. The whole thing implies f of P does not equal to f of Q. And I can put in extra parentheses just to be more readable. There we go. Okay, we know this is true. We know this is true because for both of those, the left-hand side of the implication is false already. So this is also a self-check moment, okay? If you just go like, okay, I know exactly what tag means because I remember or I have in my notes the truth table of implication, great. If you say, I think I can find out why this is the case because I know where the definition is, okay, not a problem. For people who are thinking, I have no idea why that is a one, it's a warning flag. Okay, that means you might need to step up on studying and remember and understanding the concepts from before. So now we just look at the middle two rows. Okay, the middle two row is already saying P does not equal to Q is true. Okay, so the only time the implication is true is when the right hand side is also true. So now you have to look at the mapping. It's like, what do we map 1 to? Because this is when P equals to 1. When P equals to 1, it maps to A. And then we look at Q. Q is 2 in this case. What does 2 map to? 2 also maps to A. A does not equal to A is false. Okay? So the implication itself is also false here. It is also false here. So because the implication can be false. I don't even count the number of times it is false because it can be false at least once for the entire table. That means the universally quantified expression is false. This particular function, mapping 1 to A, mapping 2 also to A, is not injective. Injection means for every element in the domain, it has to map to a unique element of the codomain. That is what injection means. All right. So that's all the time that we have today. So please, 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 read the material. At least finish reading, the injection, surjection versus bijection chapter or reading module before Wednesday. So because I'm pretty sure we can finish that entire module on Wednesday. Okay. So reading ahead of time, definitely is going to help. All right. Well, you guys have a good rest of the day, and I'll see you on Wednesday. Don't forget the homework assignment is also due on Wednesday before the class time. So don't forget to do it.